Special right triangles, specifically 30, 60, 90, and 45, 45, 90. So in higher level math classes, the triangle 45, 45, 90 and 30, 60, 90 right triangle show up 1,000 billion times. Okay, that's an exaggeration, but it shows up a lot. So what we're going to find today is the baseline model of both triangles. So the scaled down version, the simplest version that you need to memorize, which of course you will use to find all of the trig functions, sine, cosine, tangent, and the other three that we haven't talked about yet, and which you'll see in pre-calculus. So I'm not asking you to memorize trig functions. However, I am going to ask you to memorize these two special right triangles. So looking at 45, 45, 90, I gave you a little proof as to how this actually works out. We take a square, we throw a diagonal across it. That makes both of these angles 45, since half of 90 is 45. I can use my Pythagorean theorem to find the hypotenuse, which ends up being the square root of 2. So a 45, 45, 90 triangle has side lengths 1 and 1, opposite the 45-degree angles. That makes sense that they're congruent because the angles are congruent. And the hypotenuse is going to be the square root of 2. Looking at a 30, 60, 90 triangle, this is generated from taking an equilateral triangle with side lengths 2, so 60, 60, 60, 2, 2, 2. We can drop a perpendicular down to the bottom, which cuts this angle in half to 30 degrees. I can again use Pythagorean theorem to find this unknown side length. That's going to be the square root of 3. So the 30, 60, 90 triangle will have side lengths 1 across from the 30, 2, which is the hypotenuse, and square root of 3. Square root of 3 is approximately 1.7, just to let you know. It's not just the number 3, it's the square root of 3. So these two special right triangles, we are going to use in two cases. The first case we are going to use by finding their three trig functions, sine, cosine, and tangent, of each angle. So what that looks like then is I'm going to come up to the 45, 45, 90 triangle. I'm going to pick one of the 45 degrees. It doesn't matter because they're both the same. And I'm going to label my side lengths accordingly. So that makes this the hypotenuse. This would be my adjacent, and this side would be my opposite. So if I asked for the sine of 45, that is the opposite over the hypotenuse, which is 1 over the square root of 2. Now, in professional math, we don't like square roots in the bottom, so to write it in more formally, what I'm going to do is I'm going to rationalize the denominator by multiplying the top and bottom by square root of 2. On the calculator, square root of 2 times the square root of 2 just ends up being a 2, and square root of 2 times 1 is just square root of 2. So my first trig function, the sine of 45, is equal to the square root of 2 over 2. Okay, now I'm not asking you to memorize that. However, I am asking you that you should be able to memorize this triangle and then quickly label my side lengths and come up with the sine of 45 in relative quick fashion. Okay, continuing on, let's go ahead and do the cosine. The cosine is the adjacent over the hypotenuse. In this case, we have a 1 over square root of 2 again, and then by doing a similar process of rationalizing the denominator to make it more formal mathematically, we're going to get square root of 2 over 2. So the cosine of 45 is also the square root of 2 over 2, again, coming from our triangle adjacent over hypotenuse. Lastly, we'll do the tangent. Tangent is the opposite over the adjacent, so in this case it is 1 over 1, which reduces just down to the value of 1. So the tangent of 45 degrees is equal to 1. Again, not memorized, but coming from the triangle and using our basic trig functions. Okay, next, let's go ahead and do the sine of 30. Now in our triangle, we're going to start off by highlighting sine of 30, and I'm going to go ahead and label my side lengths accordingly based on this reference angle. So this would be my hypotenuse, this would be the adjacent side, and this would be the opposite. So hypotenuse of 2, adjacent of root 3, and opposite of 1. So sine is equal to, again, the opposite over the hypotenuse. We can substitute in our values 1 over 2. 1 over 2 is reduced down, and we get the sine of 30 is equal to 1 over 2. Cosine of 30 is going to be the adjacent over the hypotenuse. The adjacent in this case is root 3 over 2. That already has no square roots in the bottom, so root 3 over 2 is the cosine of 30 degrees. And lastly, if we did the tangent opposite over the adjacent, we get 1 over square root of 3. 1 over square root of 3. Much like before, we don't want square roots in the bottom, so I'm going to multiply the top and bottom by square root of 3 over square root of 3. Root 3 times root 3 is just a 3, and then square root of 3 times 1 is just a square root of 3. So we're left with the tangent of 30 degrees equal to square root of 3 over 3. Now, for the sine, cosine, and tangent of 60 degrees, what I'm going to do is I'm going to have to come back up to our triangle, and I'm now going to use the 60 degrees as my reference angle. And what that's going to do is the hypotenuse will stay, well, that was not great. Hypotenuse will stay a value of 2, but my opposite and my adjacent sides will actually shift here. So my hypotenuse, again, is still 2. So my hypotenuse is still 2. This becomes my adjacent side. So for 60 degrees, the adjacent side is a 1. And for the opposite side will, in fact, be square root of 3. So let's go ahead and do the sine of 60. Sine is opposite over hypotenuse, which in this case will be square root of 3 over 2. This is already simplified down, so we get square root of 3 over 2 is the sine of 60. Moving on to the cosine then. Cosine is the adjacent over the hypotenuse. From 60 degrees, the adjacent is now 1, and the hypotenuse is now 2, which gives us our answer of cosine of 60 degrees is 1/2. And lastly, if I did the tangent of 60, tangent is the opposite over the adjacent. Opposite side here being root 3, adjacent side being 1. So that reduces down to just the square root of 3 being our tangent of 60. So these 9 trig functions all show up in higher level math classes quite frequently. All right. Now, I am not asking you to memorize these 9 trig functions. However, if you memorize the triangle and then label your sides accordingly based on which angle of reference you're using, you can quickly and confidently generate these 9 trig functions. So part 1 of this section is knowing how to create these 2 triangles, memorizing them, and then being able to do the 9 trig functions from it. Now, the second portion of this involves using these special right triangles to go ahead and solve problems for missing sides. Now, each of these problems could just be done the traditional way by setting up a trig function, since we know an angle and we know at least one of the sides. I like to do this problem, though, using similar triangles, very similar to what we did in Unit 6. So what I'm going to start off by doing is recognizing, hey, I have a 30-degree angle. Well, if I have a 30-degree angle and that's 90, that means that this. And I know there's a baseline version of this triangle. And the baseline version of this triangle looks like such. I'm going to draw it in a similar orientation with the 90 degrees matching up, the 30 degrees, and the 60. And the baseline model of it is just what we drew up here. So across from the 30-degree angle, we're going to have a side length of 1. Across from the 60-degree, the hypotenuse rather is going to be a 2, and then across from the 60-degree angle, we're going to have a side length of root 3. So what does that mean then? Well, let's go ahead and actually try to figure out the value of u, which in this case is the hypotenuse of this triangle. If I wanted to match up sides that are similar or proportional, hey, these are similar sides, triangles, so that means that 7 root 2 is similar to or proportional to the value of 1. So I can set up 7 root 2 over 1. That should be equal to this value of u over the value of 2. Hey, I've set up a proportion that I can cross multiply and solve. Now, similarly, let's go ahead and solve for that. Let's set up the value of v. Much like before, I'm going to use the fact that 7 square root of 2 is proportional to 1, since those are the sides with the number values. And then what I can do is I can match up the side length of v with the side length of square root of 3. Now, solving this is just like what we did in the last unit. We're going to go ahead and cross multiply. So I'm going to go ahead and cross multiply in each of these cases. Multiplying with radicals is not that difficult. Let's take a look at it. I would have u is equal to 2 times 7 root 2. And for v, I would have v times 1 is v. So v is equal to 7 root 2 times square root of 3. Now, multiplying with radicals is very, very simple. If you remember that you can only multiply numbers that are outside the square root, and you can only multiply together numbers that are inside the square root. So here I have 2 times 7 times square root of 2. Since 7 and 2 are both outside of the square root, I can multiply them together, giving me 14 root 2 as my value of u. Here with v, I have a 7, a square root of 2, and a square root of 3. So I can multiply together the 2 and the 3 both underneath the square root, giving me 7 times the square root of 6. And I have my answer for the side lengths. Okay. Now, all this problem came down to was I recognized that I had a special right triangle, 30, 60, 90. I drew the baseline model of it, 1, 2, root 3. And I know that they are similar, so I can set up a proportion between corresponding sides. All right, the last problem then, we're going to do the same idea because I recognize, yes, I'm doing 45 degrees, but I also know this angle measure. It is also 45 since this is a 90-degree angle. So I'm going to draw in a 45, 45, 90 triangle with side lengths 1, 1, and root 2. That is, in fact, similar to this triangle. So I have side lengths 2 root 7 and 1 occupying the same space. So I can go 2 root 6, over 1. Those are proportional. I can set that equal to, let's solve for a first here. A and root 2. A over the square root of 2. Very similarly, we can do 2 root 6 over 1. And let's solve for b now. Let's go ahead and get b. That is b over 1. Hey, we can go ahead and cross multiply here, just like we did before, and solve. B is equal to 2 root 6 just from simple cross multiplication. For a, we need to go ahead and actually multiply 2 root 6 times root 2. We can multiply the numbers underneath the square root together, giving us 2 root 12. Simplifying further, a equals 4 square root of 3.